This is Empowering Introductory Algebra, the series created to assist students to overcome any basic algebra deficiencies and build a strong foundation leading to those college-level studies. Hi, I'm Bob Young, Assistant Professor of Mathematics at Brevard Community College. With the help of the BCC crew, we will bring you introductory algebra lessons like no other. Let's pick up where we left off and we'll show you why. Now, in the last episode, we were talking about perfect squares. Now, what makes a number a perfect square? Well, if you take something and raise it to the second power, or take that item and times it by itself, you get a perfect square. And a perfect square variable we talked about was divisible by 2. The exponents or powers were divisible by 2. So having that understanding of perfect squares is going to help us factor in the next episode now, which we're going to call special factoring. Let's go to the first graphic here. And when we talk about special factoring, we're going to start with the trinomial square. And the trinomial square usually factors into two of the same things. So I've got the general format for most trinomial squares. The first one, a squared plus 2ab plus b squared, will always factor, notice, into a plus b times a plus b. And if we write that sophisticatedly in algebra, we can call that a plus b quantity squared. And the second trinomial, a square minus 2ab plus b square, factors into two of the same things. Notice 2a minus b's, or a minus b quantity squared. So let's go to some examples here, which are really some more notes I started out with. So in the special factoring problems, trinomial squares, here's how to recognize them. And they're pretty easy to. The first and last terms are perfect squares. Okay, that's the first step, to be a trinomial square. Step 2, there must be no minus signs before the a square or b square in that general form we went over. So notice on these last two, there are no minus signs before the a square or the b square. And part 3, when we go to check these, if we multiply a times b and double the result, we get that middle term. And we'll see why that works now here in a second. So let's go to some examples, all right, with trinomial squares. So the first one, notice, we've got x squared and 9. So the first and last terms are indeed perfect squares. Now we could do our rainbows on this, of course. Rainbows always work, but these are even faster than rainbows, believe it or not, if you see that first and last term as perfect squares, because when we go to break them apart now, what two of the same the first two terms, what two of the same things will give me x squared? Xx. And since both of these signs are pluses, both of these signs will be pluses. We've seen that in the past. And what times what same two things gives me 9? 3, 3. So very nice to factor here. And notice if I take a and b, a is x and that's 3 there. If I multiply those and double it, I get 6x in the middle. Or if I were to FOIL this, I would get 3x on the outside, 3x on the inside, and that would give me the middle term. So it will check by FOILing or plugging numbers in to show the factors work. All right, second example, again, notice this format. First and last terms are perfect squares, so if you look for that first, we can go ahead and see if we can get two of the same things out of that. What two of the same things multiplies to give me the first term? 16x squared? 4x, 4x. All right, now both signs have to be the same here as well. They either have to be both pluses or both minuses. So in this case, since we have a plus on the end and a minus in the middle, I think we're going to have to go with minus minus there. And then what to get the 25? 5, 5. And again, we can write both of these answers sophisticatedly. Like when you look in your algebra book, this first one might say x plus 3 quantity squared because there's two of them. Or this one might say 4x minus 5 quantity squared. So these are special factoring trinomial square problems. Very quick to do, aren't they? I like these versus some of the others. All right, now let's look at some more. And some of you are going, oh, he's turning up the heat again. Yes, he is. You know he will here. So anything in common here? Again, the first and foremost rule of factoring is to always look to take something in common out. Is there a common number of 9, 48, and 64? I don't think so. Okay, there's no x's I can take out of each one. There's no y's, but if I look at this, the first and last terms are what? Perfect squares. Perfect squares. So when I break them up, I'll get two of the same things. What times what gives me the 9x to the 8th? Well, 3 to get the 9. X to the what powers? 4th. Because whenever you multiply same bases, you add the powers. So the first two terms would be 3x to the 4th. Both signs pluses or both signs minuses in here? Well, it would have to be plus plus here, plus plus here. And to get the last two terms to give me the 64y to the 6th, it would have to be 8 to get the 64. And what? Y cubed. That one's such a large answer, I had to crunch it in there. So there is your factored answer. And if we wrote it sophisticatedly, we could write 3x to the 4th power plus 8y cubed, quantity squared. So most of these, look what's happened. We have a trinomial square that factors into, guess what? A binomial squared. How about that? In those last several examples, we have a trinomial square starting out, binomial squared for the answer. What comes around in algebra goes around. Hot dang. Now, some of you are going, not fractions, Young. No, not fractions. Don't panic. All right, notice the first and last terms. It's trinomial square time. All right, so fractions, I'm going to make a little bit larger parentheses on this one to fit them all in. Fractions work the same way. What two of the same first terms will give me a 36 over 49th, a to the 12th? And notice that perfect square fractions contain what kind of numbers? Those perfect square numbers we talked about. So this would be 6/7 times 6/7 would give me the 36 49ths. A what? A what? A to the 6th times a to the 6th will multiply to give me a to the 12th using power rule 1. How about the signs here out there? Y'all caught on enough yet? Both pluses or both minus signs here, looking at these two? I think they're both going to have to be minuses to get a plus on the end and that minus back in the middle when I FOIL this back. All right, and to get these last two terms to give me this one, to get 1/4, 1/2 times 1/2, b squared. So this would be the factored answer, and you could write it quantity squared over there if you wanted to. Yeah. Now some people might look at this and say, Young, how do you know this checks? Well, make sure you get this middle term here. I know with fractions some of you get scared, but if you were to multiply these, we can do it. 6/7 times a negative 1/2 would give you, if you cross chopped here, a negative 3/7 a to the 6 b squared. Negative 3/7. That might be a little hard to see there. And the bottom one would also be a negative 3/7 a6b squared. And notice we'd take negative 3/7 and negative 3/7. It would check to give us that negative 6/7 back in the middle. So don't be afraid of diffractions. Now, trinomial squares, let me get that straightened up a little bit. Be careful. All right, it's the be careful time again. Now, some of you out there look at this and say, hey, Young, hey, we got a perfect square here. We got the first and last terms are perfect squares, but before you fall into that trap, and if you do, if you just start breaking that apart, you're going to hear, oh, you're going to be in trouble, all right, because there is a common number I can take out of each term. A common number that goes into 36, 96, and 64 first, and you must always first take out that greatest common factor. So what is it? Well, let's see here. How about a 4? I think 4 goes into each one of these. All right, so when we take the 4 out, and if you want to, we can go ahead and put it underneath each term, if that helps you, the greatest common factor, we get 9a squared plus 24ab plus 16b squared. And look what's left here. Oop, there it is. A trinomial square left. So sometimes you can take it out. Now, Young, what if I would have gone up here and just started factoring that without taking out the 4? Let's see what would have happened. And I'll show you real quick here. Let me sneak up here and said if we would have done that, to get 36a squared, y'all would have said 6a, right? To get the 64b squared on the end, you would have said plus 8b plus 8b, right? And this would FOIL back to give you this. Now, what's wrong with this answer? Notice inside the parentheses what? There's something in common we could still take out. So this is not considered completely factored, all right? So make sure, remember we talked about this earlier in the previous lessons, if there's a common number left in any of those parentheses, using some deep doo-doo. So be very careful, there's nothing left in common here. That would not be considered completely factored, because you can see there's some things that come out, and actually in each one, a 2 would come out of each one, and then you'd end up with a 4 out here anyway. All right, so it would come out in the wash. Once you factored it wrong, you would catch it and say, hey, there's still some more stuff to pull out, and you would get to here. All right, so now let's go ahead, break that apart into 2 of the same things, and we'll be merrily on our way here. What times what gives me the 9a squared? 3a, 3a. Both signs pluses or both signs minuses, the plus plus. What? To get 16b squared? 4b, 4b. And notice in the parentheses now, there's nothing else in common, so I can feel the power. All right, and I could write this sophisticatedly as 4 times 3a plus 4b quantity squared. Yeah, so these are some be careful trinomial squares here. All right, so we've seen some characteristics here. Now, one other be careful number 2. How does he do it? Be careful 1 and be careful 2. Not everything that looks like a trinomial square is 1. Because on this example, well, gee, Young, you got that first and last terms, it's perfect squares. But if I go to break this up, watch what happens. I get 2x, minus minus, 3y, 3y. Does that check? No, because if I go to multiply this back, I get 2 times 3, a minus 3 out here would give me a minus 6xy. Minus 6xy, that's not going to give me a minus 20 here anyway. And actually, I probably should make that a 20xy there. Let me go ahead and sneak that y in the problem. So that one is not going to give me this back. It looks like a trinomial square, but you know what they say, looks are deceiving. So how would we factor this thing, Young? All right, it's not a perfect square trinomial. It doesn't give us 2 of the same things. Well, don't forget what always works. Somewhere over the rainbow. We can get those skies again nice. All right, 4 times 9, 36. Factors of 36 that will add to give me 20 in the middle, you would find minus 2, minus 18 once you get good. And I tell you, the more you practice this rainbow technique here, boy, you will get surprised how quickly you can get those numbers, because they seem to like go round and round. All right, so now we can come down here and we can say to get 4x squared, we could either have 4x and x, but we know that 4 times nothing here is going to give me one of those. So we'll go 2x, 2x. All right, and now we can force those rainbow numbers. 2 times what gives me the minus 2? We'll put minus 1y there since there's a y on the end. So we've got our minus 2 on the top rainbow. And then this will give us, what will give us minus 18? 2 times what in here will give us the minus 18 will be minus 9y. See, so in this case, it looked like it was a trinomial square, but when we factored it, we didn't get 2 of the same thing. So be careful. Be careful.